Now we're going to solve some forced harmonic oscillator problems using this method of undetermined coefficients. So let's start with our problem. The second derivative of y with respect to time plus 7 times the first derivative of y with respect to time plus 12 times y is equal to e to the negative 2t. So we're going to drive this spring by the function e to the minus 2t. And let's let the value at time 0, we're going to give some initial conditions here. The value at time 0 is going to be minus 1/12. And the value of the derivative at time 0 is going to be 7/6. Okay, so the first step to solving these problems is solving the homogeneous problem. And to do that, we take a look at the characteristic polynomial. Lambda squared plus 7 lambda plus 12 equals 0. We see this factors into lambda plus 3 times lambda plus 4. So the eigenvalues are lambda equals minus 3 and lambda equals minus 4. So that immediately gives us the homogeneous solution, which is some constant k1 times e to the minus 3t plus another constant k2 times e to the minus 4t. Okay. Now we want to solve the particular problem, so we need to make a guess. And our guess is going to be some constant k that we don't know times e to the minus 2t. All right, that's what we're looking for, k times e to the minus 2t. Now, if this was a solution, then we could plug it back in to this equation, the original equation, and get something true. So that's what we're going to do. The second derivative of k times e to the minus 2t is 4k times e to the minus 2t. The first derivative of k times e to the minus 2t is negative 2k times e to the minus 2t. And so that negative 2 is going to be multiplied by the 7 and give minus 14 times k times e to the minus 2t. And then we will have plus 12 k e to the minus 2t. And that's supposed to all equal e to the minus 2t. We've done it right. So let's see. So 4k e to the minus 2t minus 14k e to the minus 2t plus 12k e to the minus 2t. Well, altogether, right, we have, that looks like about 2k e to the minus 2t is equal to e to the minus 2t. So that immediately says, okay, well, k must be 1/2. So that means my solution, y of t, is equal to the particular solution, which is 1/2 e to the minus 2t. This solves the equation, plus any homogeneous solution. So k1 e to the minus 3t plus k2 e to the minus 4t. Now simply what we need to do is plug in 0 for y, and then also calculate a derivative and plug in 0 for y prime. And then we'll have to choose k1 and k2 to match the initial conditions. Y of 0 is minus 1/12, and y prime of 0 is 7/6. And that will solve the problem. So this is what happens when the driving term is not a part of the homogeneous solution. let's take a look at another example. It's actually going to be the same example, but here the driving term is going to be part of the homogeneous solution. So let's see what happens when we do that. Here, we're going to start again with the same differential equation, except the driving term is going to be different. Now the driving term is going to be e to the minus 3t. So recall we had the homogeneous solution, right? The coefficients are the same, so the homogeneous solution is the same problem. It's going to be k1 times e to the minus 3t plus k2 times e to the minus 4t. Now, if we try to make a guess, let's do the wrong thing. Let's guess a constant times e to the minus 3t and see what happens. Okay, when we do that, we first take the second derivative, because of this here. We take the second derivative of that, and that would be 9k e to the minus 3t plus 7 times the first derivative, which will be minus 21k e to the minus 3t plus 12 times e to the minus 3t times k, so 12k. And we need that to be equal to e to the minus 3t. But it can never be equal to that because 9 minus 21 plus 12 is 0. So there's no k that's going to work. This will happen if the driving term happens to also be one of the terms that solves the homogeneous equation. So what do? We must reform our guess. We make a better guess. And here our guess is going to be k times t times e to the minus 3t. Okay. When we do that, this becomes a little more difficult in the sense that we have to take two derivatives of this term, and of course the product rule is involved. So I'm going to put down the first derivative here first. The first derivative is going to be k e to the minus 3t plus, or rather, minus 3kt e to the minus 3t. We're going to have 12 kt e to the minus 3t. This is all supposed to equal e to the minus 3t. I've left this over here blank because I need to fill in the second derivative, and it's easier to write the second derivative if I have the first derivative sitting right here. The second derivative then is going to be, let's see, we get 9 kt e to the minus 3t minus 6k e to the minus 3t. Now I've simplified it already, right? We get a negative 3k e to the minus 3t, and here we get another negative 3k e to the minus 3t when we differentiate t. Then when we differentiate the e to the minus 3t, we get this positive 9k term. Now you'll notice, how many kt terms do we have? We have 9, minus 21, and 12. Look, it's the same here, 9, minus 21, and 12. That's going to happen every time. So that's going to automatically be equal to 0. So it's only the k terms that matter without the t. And when we add those up, we have minus 6 of them here. And we have 7 of them here. So we have a total of k times e to the minus 3t is going to equal e to the minus 3t. Oh, so k is equal to 1. So the general solution for this equation, hopefully I've got room here, is t e to the minus 3t plus the homogeneous solution, k1 e to the minus 3t plus k2 e to the minus 3t. And then depending on if you're given initial conditions, I did not write any here for this problem, but if you're given initial conditions, now you can use those to figure out what k1 is and what k2 is. So that's how you solve these forced harmonic oscillators in either instance, whether it's driven by an eigenvalue solution or not.